Hello, welcome to the lecture series on control systems engineering. Let us continue our discussion on time response analysis. In this session, let us define transient response specifications of second order and higher order systems, derive mathematical equations for delay time, rise time, peak time, maximum overshoot, and settling time. Let us solve a few simple and complex problems which involve fixing of design parameters to achieve defined time response specifications. And let us demonstrate time response behavior with parametric variation using MATLAB and Simulink. Here I have shown the output response, the response of a second order system subjected to unit step input. This is the input. And this is the response of the system. This is the response of the system. Like this. Okay. This is time t. This green curve is output versus time, red characteristics is input versus time. RFT versus time. Now, time taken by this response to show 50% of the output. This one. This is the 50% of the output. This we call it as delay time. This we call it as delay time to show 50% of the output. Time taken by the response to show 100% of the output. This one. This we call it as rise time. Okay. Time taken by the response to reach to the peak of the response. Here. This we call it as peak time. Then this is the input value. There are many overshoot. This one is the maximum one. This we call it as maximum overshoot or peak overshoot. Then response oscillates like this. When it has shown 95% output or 98% output, then we call that time as settling time. Okay. So more accuracy if you are looking for the 98%, otherwise it's 95%. That we call it as settling time. These are known as time response specifications. We can specify to what output, what peak overshoot we should have, what settling time we should have, then we can design the system parameters if we specify this. So these are known as time response specifications. So delay time, it is the time required for the response to reach 50% of the final value in first attempt. Rise time, it is the time required to rise from 0 to 100% of the final value. Peak time, it is the time required for the response to reach the peak of time response or the peak overshoot. Settling time, it is the time required for the response to reach and stay within a specified tolerance band, 2% or 5% of its final value. Peak overshoot, it is the normalized difference between the time response peak and a steady output. Okay, it is this. So it's a maximum response, steady state divided by steady state. This we call it as peak percentage peak overshoot. Okay, let us find the expressions for rise time. We know this equation already. I have derived this. C of t is equal to 1 minus e to the power of minus zeta omega nt So in this equation, the value of t, this t will be tr, then the value of c of t will be 1. So I'll substitute in place of c of t 1. This is 1 minus e to the power of minus zeta omega n, t becomes tr. This is cos omega t omega d tr plus zeta under root 1 minus zeta square sin omega d tr. So this 1 minus 1 will become 0, 0 divided by this will become 0. Then we will get cos omega d tr plus zeta under root 1 minus zeta square equal to 0. Okay, move it to the right hand side. Then divide. You will get tan omega dtr is equal to minus root of 1 minus zeta square by zeta. Then omega dtr is equal to tan inverse of minus root of 1 minus zeta square by zeta, that is minus tan inverse. So we have to find time taken for the response to rise from 0 to 100%. So we are getting this value, we should get this value. That's why I subtract from pi minus tan inverse of root of 1 minus zeta square by zeta. Okay, then this omega d comes out. So this becomes the rise time equation. Okay, remember pi minus tan inverse of root of 1 minus zeta square by zeta by omega t. So it should be in radians. That's very important. So we'll get rise time in seconds. Okay, right. Similarly, we'll find peak time, Tp. Again, we have got the equation C of t is equal to this. We know this. We have derived this equation. T becomes Tp because at the peak point, the slope is 0. So dc of t by dt will be equal to 0. There is a maximum. So let us differentiate this and equate it to 0. If I differentiate this equation and equate it to 0 and replace t by Tp, you'll get sin omega dTp equal to 0. This sin omega dTp to be 0, omega dTp should either be 0 or it should be pi or 2 pi like this. So this cannot be 0, so we'll take that first pi, right? So then Tp will become pi by omega t. Okay, this is peak time. It is again in seconds. Now maximum response. Again we have this equation. In place of t, let us substitute Tp value. So here Tp nothing but pi by omega d, I'll substitute over here. Okay. So sin pi is 0, cos pi is -1, so minus up minus it will become plus. So you'll get this one. But omega d is again omega n under root 1 minus zeta square. This 2 will cancel. You will get C of t maximum, this value. Okay, right. That is the maximum response. That is this height. 1 plus that value. E to the power of minus zeta pi under root 1 minus zeta square. So maximum overshoot is C of t maximum, and subtract that steady state value, you will get this MP you have got. So multiply with 100, you will get percent overshoot. So time constant is defined as 1 by zeta omega n second. How do we get this? You know, already have done for first order system time response equation, that is 1 minus e to the power of minus t by capital T. If I compare with this, 1 by t is equal to zeta omega n. Correct? So t equal to 1 by zeta omega n. That's how you get that value. Also we have proved with t is equal to 3 time constant, then there will be 5% error. For 4 time constant, it will be 98% output, 2% error. Okay, so this we are done in our earlier session for first order system. So I am just borrowing that here. Okay, now you have got the equation to find rise time, peak time, overshoot, then time constant and settling time. All these equations you have. So now you should be able to work out some simple examples. Let us consider a simple example now. Consider a system for which omega n is 5 radians per second and zeta is equal to 0.6. These are given. Then determine the rise time, peak time, overshoot, settling time. Just substitution into this equation. Rise time pi minus tan inverse root of 1 minus zeta square by zeta omega d. Omega d is nothing but omega n under root 1 minus zeta square. Substitute, you will get this. Okay, all the values you substitute and you'll get the rise time. Peak time is pi by omega d. So omega d value, you know, you can find out this 0.785 second. Overshoot is e to the power minus zeta pi under root 1 minus zeta square. You substitute the values, you will get the overshoot. So percentage overshoot is 9.4%. For 3 time constant, settling time is 1 second, 3 by zeta omega n. For 4 time constant, for 2% error, it becomes 1.33 seconds. Sorry for the quality of the slides, but still I feel you can read them out. The forward transfer function of a unity band feedback system is given by, that is G of S is given. 25 divided by S into S plus 5. Determine the following: natural frequency, damping ratio, damped natural frequency, rise time, percent overshoot, and approximate 5% settling time. So the idea here is take our standard block diagram R of S. This is G of S. This is C of S. This is plus. This is minus. H of S. Like this. Problem states it is 25 divided by S into S plus 5. So it's unity feedback. So H of S is 1. So you will get C of S by R of S equal to G of S divided by 1 plus G of S. Done this. You compare with the standard form. So omega n square is equal to 25. Omega n is 5. Then 2 zeta omega n is equal to 5. Then calculate zeta. Okay, that becomes 0.5. After that, it is direct substitutions. Damped natural frequencies omega n under root 1 minus zeta square. You will get this. Rise time is substitute into this formula. Right. So zeta, all the values when you substitute, you will get this. Percentage overshoot, again if you substitute into this formula and calculate, you will get. TS is 3 settling time, so you will get 1.2 seconds. So you should remember the formula. For the system shown in figure, determine the following. Again, natural frequency, damping ratio, damped natural frequency, time constant, settling time. The problem given here is 25 divided by S into S plus 7. So the same thing, compare with it and you get the values. Here the forward transfer function of a unity feedback system is G of S equal to K divided by S into S plus 10. Determine the following quantities. 1. K if the damping ratio is 0.5, percent overshoot and time to peak overshoot. That is the thing. So here K is given, which is unknown. So now this you compare with this one, K becomes equal to omega n square. And 2 zeta omega n is 10. So omega n will become 10 by 2 zeta. Zeta value is given. So omega n will become 10 radians per second. Then substituting here omega n value, you will get K value. So then MP, this equation is given. Now the values are known. You can find out the overshoot. And peak time, this formula is known. Substitute the values, you will get this value. Next, a second order system is characterized by a second order differential equation. Y double dot 8y dot 25y equals 25x. What is the maximum response of the system if it is subjected to unit step input? You know, maximum response equation is this one. The whole thing is from this equation, you have this. If you take Laplace, you find the transfer function, you'll get 25 divided by s square plus 8s plus 25. Compare with it, you'll get omega n value. Then 2 zeta omega n is 8. Find zeta value and substitute. Okay, very simple example. A first order system is characterized by the transfer function C of S by R of S is equal to 1 by S plus 4. Find the time response to the system if it is subjected to unit step input. Also find the time constant. It's a first order system. So C of S by R of S is equal to 1 by S plus 4. Subjected to step input 1 by S. Then split it into partial fractions, right? You get this. Then you will be getting the values of A and B. Substitute back into this and take inverse Laplace. Okay, you will get this. So obviously t by t, capital T is equal to 1 by 4. Time constant is 1.25 seconds. Okay. A first order mechanical system has a spring of 2.5 Newton per centimeter and a damper of 0.5 Newton second per centimeter. Okay, K is given and C is given. Determine the time constant. You know F by K or C by K is the time constant. Subject is step input. If it is suddenly pulled by 4 centimeter, what is the time response to the system? What time will the response be? 80% of the steady state value. Okay, time constant is F by K if I use F, or if I use C here, C by K. This is C or F. This is K. So we know this. We have defined this. So this is the transfer function of this system. Then it is 4 by S is the input. Then carrying out partial fractions will get A value and B value. Substitute back into this, take inverse Laplace, we'll get this. Okay, right, sir. Now output is 80%, put 80% of the output here. So from that we can calculate time. Okay, this is log ln. Okay, natural log. Here I have given an example k 1 by s square 1 plus k, small k, it is capital K. Shown in figure, determine the values of k and k so that the peak time is 2 seconds and overshoot is 25%. First get the transfer function, I'll get it. Then k equal to omega square, capital K and small k is equal to 2 zeta omega again. So then zeta is equal to small k is equal to 2 zeta omega n by capital K. Okay. Now for us he has given MP. Okay. Sorry, MP is given. Since MP is given, I can calculate zeta by taking log on both sides. Natural log. Okay. So I got the zeta value. Next, Tp is pi by omega d, that is also given. Omega d is omega n under root 1 minus zeta square. From that I can get omega n. Once I get omega n value, and I can get the values of capital K and small k. Again another example. For the system shown in figure, determine the values of K and KH. Peak time is given as 1 second, overshoot is 0.2. Also find the settling time and rise time. A similar example. So get C by R. From that compare with omega n squared, then you will get what is K, what is KH. Now find the zeta value and omega n value. So overshoot is given, I can find zeta value. Correct. Peak time is given, I can find omega n value. Then I can find K and KH. Then if I substitute in this equation, I'll get the time constant. Then I can find settling time for 5% error criteria and settling time for 2% error criteria. And in this equation, if you substitute, you will get the rise time. You have to just calculate. That's all. A first order system is characterized by the differential equation 0.5 df by dt plus f is equal to 5t. As f equal to 0 at time t is equal to 0. Determine the total response of the system. This is the initial condition given. Okay. So df by dt plus 5t. So take Laplace, it becomes 0.5 s f of s, this is f of s, this is equal to Laplace of t is 1 by s square. So f of s I have got like this. It is subjected to, ramp input. phi t is there, at. So split it to partial fractions and take inverse Laplace. Okay. The forward transfer function of a unity feedback system is g of s equal to k divided by s into ts plus 1. Determine what factor k must be multiplied in order to reduce the overshoot from 75% to 25%. Right now, initially the overshoot will be 75%, then you have to reduce it to 25%. So when you reduce it, you will get like this. Right, you can compare with this. You have to get zeta value. So omega n square is equal to k by t. Omega n is root of k by t. 2 zeta omega n is 1 by t. So zeta is 1 by t to omega n. Again substituting for omega n, you will get like this. Finally, zeta is equal to 1 by 2 root kt you get. Okay. So MP is this, so it is initially 75%. So you'll get zeta is equal to 0.85. Next, it should be reduced to 0.25. So what should be the value of zeta? I should increase the zeta to this value. So zeta 1 is this, zeta 2 is this. Take the ratio and you will get this. K2 should be K1 by 20.6. So K must be multiplied by 1 by 20.6 in order to reduce the overshoot from 75% to 25%. This gives an idea, like, while designing the problem, what needs to be done, what manipulations have to be done. A second order servo has a natural frequency of 6 radians per second. Sufficient velocity feedback is added to the system so that the response to a step input is just non-oscillatory. That means zeta should become equal to 1. Find the gain of the system for a sinusoidal input of frequency 0.1 cycle per second. So C of s by R of s is this. So I have to convert into frequency. That's why I have substituted s is equal to j omega. Then I have got this equation. Then j square is equal to -1. Then I have found out the magnitude. So magnitude of this is the real part, this is the imaginary part. It should become square root of square of real part and square of imaginary part. So omega n is 6 radians per second, zeta equal to 1, omega is this thing. Substituting, you will get m is equal to 0.998. Right. So, okay. Now you know how to find the parameters using those equations. So let us study the characteristic. Okay. In most of the practical situation, the systems are designed to be underdamped. Since overdamped systems are sluggish in their response, you have seen that. Achieving and maintaining critical damping virtually not possible. So design issue hence will be to tune the system parameters to achieve suitable underdamped characteristics. What it means we'll see now. You have seen this. For an underdamped case, S1, S2 is equal to minus zeta omega n plus or minus j omega n under root 1 minus zeta square. Correct? Or you can also write this as minus zeta omega n plus or minus j omega d I can write. This is real part. This is imaginary part. So this is the real part. So this I can call it as, if you want, minus sigma d plus or minus j omega t. Okay. Imaginary part is omega n under root 1 minus zeta square. So you will get one root here and another root here. So this square, this length is zeta omega square, plus this square is nothing but omega n hypotenuse. So let us understand that now. Okay. Suppose if I write cos theta is equal to zeta omega n by omega n. So cos theta represents zeta. Correct now? Or zeta is equal to, I can say, cos inverse theta. Sorry. Cos inverse theta. So that means this is, let us say, theta is equal to 0. Theta is equal to something. Theta is equal to something. Right? Like this. So this can be cos 0 is 1. Correct now? So zeta is equal to 1. Zeta is equal to something, maybe it can be 0.1, 0.2, like this. The zeta value decreases. And the zeta value will be here according to this. This is zeta equal to 0. So these are constant zeta values, lines. So when the roots are here, the response will be oscillatory. The system will be responding with constant amplitude. As you start moving like this, the amplitude keeps decreasing. Moment it reaches, it will not oscillate at all. Correct? These are all constant zeta values. Okay, fine. Right. Now, let us say keeping zeta omega n constant. Let me later. Okay. So this, I hope you understood, these are constant zeta lines. Let us go to this. Peak time Tp is pi by omega t. Correct now? Let us take this coordinate system. Okay, in this coordinate system, it is sigma j omega. This is sigma, this is j omega. Omega n is nothing but, omega d is nothing but omega n under root 1 minus zeta square. So omega n under root 1 minus zeta square. So this is one value, let us say, another value, let us say, another value, let us say, another value, let us say. So suppose if I keep on increasing this value, peak time decreases. Correct now? If I go on increasing this value, if I go on moving in this direction, means if I go on making my imaginary part larger and larger, means peak time decreases. What's the meaning of that? Suppose this may be a peak time. Next value, if I increase, peak time may become like this way. It will start moving in this direction. Correct? If the imaginary part, if I keep on increasing. Okay, you can say these are constant peak timelines, right? So it won't matter what is the imaginary part. It depends only on, real part. It depends only on the imaginary part. So this is why these are all constant peak timeline. But as you move outwards like this, peak time decreases. So peak time TP is inversely proportional to the imaginary part of the pole, correct? Right. As imaginary part increases, the peak time decreases. It becomes faster. Right. Probably, if we can look at this, suppose, let us say, a point here, you can see, suppose I have a point here, this theta increasing. That means this zeta is less compared to this. So that is the reason why it happens like that. Okay, fine. Now settling time, Ts is equal to 4 zeta omega n. So zeta omega n is this part. Okay, suppose if I go on decreasing this zeta omega n value, then what is going to happen? Zeta omega n value, if I keep on reducing, settling time will increase. Correct now? So Ts is inversely proportional to the real part of the pole. So you can say these are all constant settling timelines. Okay, so that's how I have got it. Settling timelines. Right. So you have understood all these things. Now, poles are moved in vertical direction. So now let us look at this. I am moving like this. Poles means roots of those equations. Poles means roots of this equation. So this is omega d. That is nothing but omega n under root 1 minus zeta square. As I said, if I go on increasing this value, I said overshoot should decrease. Correct now? Sorry. These are constant peak time now. So I said the peak time should reduce. Correct. peak time should reduce. You see here now. If I draw a line like this, maybe this is the peak time. If you move up, peak time decreases. Move up, peak time decreases. Okay, the frequency changes, the envelope remains the same. The settling time is virtually the same for all waveforms. I said this is a constant settling timeline. That is also there. Okay, right. I am moving them, means what is going to happen? Settling time should increase now. Okay, so 1, this is the settling time. 2, so what is settling time? 1 by zeta omega n, time constant. So zeta omega n increases, time constant should decrease. So settling time should decrease. That's what's happening. As you move like this, settling time should decrease. Here the settling time is so much. Here the settling time is so much. Yeah, this kind of understanding is very important. So now we can understand where exactly we need to keep the roots. Suppose if I know the root value, then you can find what should be zeta value, what should be this value. If I know omega, zeta value is known, omega n value is determined, then we can go backwards and we can find the system parameters. That way it becomes very easy. Knowing the pole locations, it becomes easy for us to set the time response specifications of the system. That's why this understanding is very important. Now what's happening here in this case? I think theta, the zeta is remaining constant. So both omega n this way also it is increasing, this way also it is increasing. If I said this way it should increase, means settling time should decrease. Settling time should decrease. If I move like this, peak overshoot should decrease. So here what's happening? 1. Okay, but the overshoot is remaining the same, right? But setting times are changing. Okay, so as you move towards left, that's what's happening. It's settling very fast. Correct? Settling very fast. Compared to 1, you see 3 is settling fast. Compared to 1, 2 is settling fast. Compared to 3 is settling fast. Okay. Example of finding zeta, omega n, tp, percent overshoot and settling time from pole location. This pole is given. This pole is given. Means complex conjugate poles are given. I mentioned earlier how we can arrive at a response specifications. Correct. Pen. Next is ink color. I'll take. So once this point is given, draw this vertical line. Draw this line also. This is given, so zeta is equal to cos theta. So theta value, if I know opposite adjacent side and opposite side height, that is my 3 and 7. So theta I know, so I can find out zeta. See, adjacent side is there, opposite side is known, means I can find out the hypotenuse, so I can find out cos theta, no problem. But also zeta is known. Sigma d is nothing but zeta omega n. The zeta omega n equal to 3 means zeta is already known, omega n I can find out. Or this is nothing but omega n. Omega n nothing but square root of this plus this. Okay, I have got this, then other things, all these values. You can just substitute and get it. Correct. Now C of S by R of S is equal to omega n square S square plus 2 zeta omega ns plus omega n squared. Okay, you just compare this with k by m, correct now, s square cr f by m s plus k by m. So now these values are known, I can find k, then I can find c, I can find m also. So then I can design my physical system which will have these characteristics. So it's reverse. So if you know the pole locations, what kind of response you want, based on that I can achieve this. Okay, hope you have understood how these poles, means the roots of this characteristic equation, play a very important role in time response specifications design. This is a very, very important thing a control engineer should know. Now let us, you can also see this kind of response. After that, if you want, you can simulate using MATLAB. And it is always possible to find all the time response specifications in MATLAB. Okay. Hope you have got a clear understanding of time response and its importance. So the behavior of higher order systems will not be very much different from the second order system. So once you learn how to design the system for required response, then you can always realize this in form of a physical system. So this one part, like in the control system, I said it should meet three requirements. One is stability, relative stability, and accuracy. So this, what I discussed now, is the response, that is more about relative stability. In the next topic, we'll talk about how to determine system stability. Okay.